At its core, machine learning shifts the paradigm from writing explicit rules to creating systems that learn from experience. Think of supervised learning as a student learning with an answer key. The algorithm is provided with labeled data, where each input is paired with the correct output. This process generally falls into two categories: classification and regression. In classification, the model learns to assign data to specific categories, like distinguishing a cat from a dog or identifying a fraudulent transaction. In regression, the goal is to predict a continuous numerical value, such as estimating the price of a house based on its square footage or forecasting tomorrow's temperature. By minimizing the error between its prediction and the actual label, the model slowly refines its internal parameters to better understand the relationship between features and outcomes. But what happens when we don't have an answer key? This is where unsupervised learning comes in. Here, the machine looks for inherent structures or hidden patterns within unlabeled data without any guidance on what the correct result should be. A common technique is clustering, where the algorithm groups similar data points together based on shared characteristics. Imagine a retailer analyzing customer purchase histories to discover natural market segments. The machine doesn't know the names of these segments, but it can see which customers behave similarly. Beyond finding groups, we have reinforcement learning, which is inspired by behavioral psychology. In this scenario, an agent interacts with an environment and receives reward signals for its actions. It learns through trial and error, much like an AI learning to play a complex strategy game or a robot learning to walk. The goal isn't just to match a label, but to maximize the total reward gathered over time. The life cycle of any machine learning model is divided into two distinct phases: training and inference. Training is the computationally heavy phase, where the model studies the data to find patterns and adjust its weights. Once the model is optimized and the learning phase is complete, we move to inference. This is where the model is deployed to the real world to make predictions on new, unseen data. However, a major hurdle in this process is a phenomenon called overfitting. Overfitting occurs when a model learns the training data too well, effectively memorizing the noise and specific quirks of the dataset rather than the actual underlying patterns. It's like a student who memorizes the exact answers to a practice test but fails the actual exam because they don't understand the core concepts. Achieving a model that generalizes well to new situations, rather than just repeating what it has already seen, is the ultimate goal of any practitioner.